Okay, so let's continue our discussion with the systems that has damping. So we learned that the roots can be found as negative lambda plus or minus square root of lambda square minus w square. Now when lambda square minus w square is equal to 0, this part vanishes, becomes 0. So the only root is actually negative lambda. Well, it's two roots actually, it's repeated. Alright, now it's repeated. What are the two solutions in the fundamental set of solutions? So remember, this is a second order differential equation. So you have y1 e to the negative lambda t, right? And the second solution, how do you find it? Remember, when you have repeated roots, it's t times e to the negative lambda t. Now, the notation could be a little bit weird for you because in section 4.3 we use x as independent variables. So remember, we multiplied by x in the section 4.3, but here the independent variable is simple t. So I think it's a smooth transition from section 4.3. Make sure that you translate very well from section 4.3 to this section. Okay, so then the general solution we can write as a, no, not the y, right? So see, I didn't do the transition properly, right? So it's x1 and x2, the fundamental set of solutions. Anyway, so the solution is actually c1 e to the negative lambda t plus c2 t e to the negative lambda t, right? Okay, so this is the solution. Now we say this system is a critically damped system when lambda is equal to w square, or lambda square minus w square is 0. Now you can ask, well, what is the difference between over damped system and critical damped system? Because if you look at the solution of a critical damped system, it's similar to what you have in over damped system, except you have this t. Now the limit of this displacement is again 0 because these are all exponential decay, right? So because you have exponential decay, you approach to 0. So again, it's same as consistent with over damped system. But the difference here, in critically damped system, you achieve to the rest position or the equilibrium position very quickly than over damped system, or later we are going to learn under damped system. But critically damped system will approach to equilibrium position fast than other two cases. Okay, so this is a fast approach. You take a minimum time to approach to the 0 or the 0 displacement or the rest position. So that's the difference. Okay, so let's look at an example and understand some of the things here. Okay, so here, well, first we have K is 10 grams over second square and the mass is actually 10 grams. So the W square is 10 over 10, K over M, 10 over 10, it's 1, right? Okay, good, nice numbers. Then we have to find the 2 lambda, the proportionality constant is beta is 20, so 20 divided by mass 10 is 2, so beta divided by m is 2, so 2 lambda is 2. So we can formulate the differential equation as this. So 2 lambda is 2 dx over dt plus w square is 1, so x is equal to 0. Okay, good. Now the initial conditions seems to be like, well, if the mass is pulled down 5 centimeters, so that means x0 is 5 with a speed of 10 centimeters, so speed is x prime, which is 10. All right, so we have the initial value problem, so let's solve it here, starting from here. Okay, now we write the auxiliary equation, so m square plus 2m plus 1 is equal to 0. So if you factorize, try to pause this and do it, okay, which will be m plus 1 square is equal to 0. So the root is actually negative 1 repeated twice. So the solution is c1 e to the negative t plus c2 t times e to the negative t. Okay, all right, so let's use the initial conditions. So when t is 0, x is 5, so c1 e to the 0 is 1 and t is 0, so this term is 0. Nice, right? So you get C1 right away 5. So I like these problems. Great, right? So let's find C2. Then you have to use the second condition. So you have to find the x prime, right? Because the second condition is for x prime. Oh, well, that's not going to be a little bit difficult. So if you want to differentiate this, here negative comes out. So negative C1 e to the negative t. Here you have to use product rule. So if you differentiate t first, it's C2 e to the negative t plus differentiate e to the negative t. So this is negative C2t e to the negative t. So that's x prime. So if you use this condition, when t is equal to 0, x prime is 10. So negative C1 plus C2 t is equal to 0. So that terms disappears. So C1 we already know 5. So if you take negative 5 to the other side, C2 is actually 15. Alright. So actually the general solution then is not the general solution is this. The solution is 5 e to the negative t plus 15 t e to the negative t. So that's the solution of this problem. Okay, so again this is a critically damped system. Now if you plot this solution, you can see the behavior is quite a bit similar to over damped system, but always remember critically damped system are the systems where you approach to equilibrium position quickly rather than the other two cases. But again, if you look at the solution is dominated by really exponential decay functions. So you will have an exponential decay behavior just like here dominated in your solution graph, right? And it makes sense. So that's the critically damped case. So in next video, let's learn the under damped case. Okay, all right, thank you.